This video explores the translation bridge between human-readable Python code and the physical hardware that executes it. How does a high-level interpreted language actually communicate with microscopic transistors to perform calculations?
Python, being a high-level interpreted language, requires a software middleman to communicate with the silicon hardware. This middleman consists of the Python virtual machine, or PVM, and the computer's operating system, or OS, which translate instructions for execution. We will examine the 5-step lifecycle of a line of code, following the mechanical and software steps triggered by the simple assignment, x = 5 + 3. This includes code translation, memory allocation, virtual machine processing, hardware execution, and cleanup. Step 1. The CPython compiler translates the source code, which the hardware doesn't understand, into hardware-independent bytecode. This bytecode is a set of instructions exclusively for the Python virtual machine, not for the CPU. Step 2. The operating system carves out a chunk of RAM for Python's exclusive use, called the private heap. The Python memory manager handles this memory, meaning programmers cannot directly access this raw memory space. In Python, every simple number is treated as a complex object stored in the private heap. The memory manager carves out blocks to store the integer value, its data type, and the reference count. Step 3. The Python virtual machine, a massive loop written in C, reads the bytecode instructions one line at a time. It translates human logic into discrete mechanical steps for the software to process. Because CPython is written in C, the PVM translates the bytecode instructions into underlying C functions. The operating system has already compiled these C functions into machine code, or ones and zeros, tailored to the specific CPU architecture. Step 4. The operating system schedules hardware execution. The software translation is now complete. The OS queues the Python program for physical time on the CPU, starting the continuous loop of fetching, decoding, executing, and storing data. During the fetch and cache stage, the CPU requests data from the slow RAM. To prevent bottlenecks, data is pulled into the CPU's internal L1, L2, and L3 caches, and finally into the CPU's registers for immediate, lightning-fast processing. In the execution stage, the arithmetic logic unit, or ALU, receives the electrical signal to add the two registers. Transistors physically open and close, crunching the binary addition to produce the result, which is then immediately sent back out to the RAM. Step 5. The cleanup and pointer assignment. Control returns to the Python memory manager. Python creates a new object in RAM for the result and points the variable name x directly to that memory address. If you overwrite a variable, the original object's reference count drops to 0. Python's garbage collector instantly frees up that physical space in RAM for other programs to use. This sequence shows the complete translation bridge, demonstrating how a single line of code triggers an intricate ballet of software translation, memory management, and physical transistor execution. The true elegance of the abstraction layer is that Python's greatest trick is hiding the millions of mechanical and software operations behind a single line of human-readable text. The PVM, OS, and memory manager handle the logic, allowing you to focus purely on programming.